Ever stop to think about what's really going on inside your phone? I mean, we say electricity, but what is actually moving around in there to make it all work? Well, today, we're going to pull back the curtain on the secret life of semiconductors and meet the tiny messengers that power our entire digital world. Let's dive in.
Think about it. The CPU in your computer, the RAM in your phone, the tiny LEDs that make up your screen, even solar panels soaking up the sun. They all seem like totally different technologies, right? Well, deep down they all run in the exact same fundamental secret: how electricity moves at the tiniest possible scale.
So, that leads us to the big question for today. What is actually zipping around inside these chips to make everything happen? The answer is, well, it's surprisingly simple and at the same time, just a little bit weird. To get that answer, we need to meet our two main characters. They're called charge carriers, and they're the particles, or in one case, the absence of a particle, that do all the heavy lifting in our tech. A charge carrier is pretty much exactly what it sounds like. It's a tiny, mobile thing that carries an electric charge from one place to another. Now, in a simple copper wire, that's really just electrons. End of story. But inside a semiconductor, oh, that's where the story gets so much more interesting. Because in the world of semiconductors, it's not just one particle doing all the work. No, there are two key players on the field, and understanding both of them is the key to, well, everything that comes next. On one side, we've got the good old electron. We know this one, right? It's a real physical particle, and it has a negative charge. Simple enough. But on the other side, we have something called a hole. And this is where your brain might do a little flip. A hole acts like it has a positive charge, but it's not a particle at all. It's literally just an empty space. So wait a minute, how can an empty space, a particle that isn't even there, actually carry an electric current? That sounds impossible, right? But I promise you it's one of the most important concepts in all of electronics. Let's break down exactly what a hole is and how it moves.
At its heart, the definition is this simple. When an electron sitting in its designated spot in a semiconductor gets a little jolt of energy and breaks free, it leaves behind a vacancy. That empty spot, that missing electron position, that's what we call a hole. And this gives us the perfect way to think about it, the empty seat analogy. Imagine a row of seats in a movie theater, all full. One person gets up and leaves. That empty seat is our hole. Now, the person sitting next to it decides to slide over into the empty seat. Has the hole disappeared? No, it's just moved over one spot. Then the next person slides over, and the hole moves again. See? The people are moving one way, but the empty seat appears to be moving in the exact opposite direction. That's precisely how a hole moves. So let's do a quick recap of the key differences here. The electron, it's a real negatively charged particle that physically moves. The hole, on the other hand, is not a real particle. It's just the absence of an electron. And its movement is just an illusion, an apparent movement. And because it's a spot where a negative charge should be, it behaves for all the world like it has a positive charge. This two-carrier system is the absolute magic behind semiconductors. Okay, so we know what our charge carriers are. The next big question is, how do they actually get around? What makes them go? Well, it turns out there are two primary ways they move inside a material: drift and diffusion. First up is drift. This is the one most of us think of when we imagine electricity. You apply a voltage, say from a battery. That creates an electric field, and this field literally forces the charge carriers to move in a specific direction. You can think of it like a river. The electric field is the current, pushing everything along. It's a controlled march. The second way they move is diffusion, and this one's completely different because it doesn't need any external force. It's just a natural tendency. If you have a whole bunch of electrons crowded together in one area, they will naturally spread out into the areas where there are fewer of them. It's just like dropping a bit of food coloring into a glass of water. It naturally spreads out until it's evenly distributed. So, to boil it all down, drift is a forced, controlled march ordered by an outside voltage. Diffusion is a natural, random spreading out from a crowded area to a less crowded one. And the crazy part is, both of these movements are happening all the time inside your devices. All right, so we've met the carriers, electrons and holes. We know how they move, drift and diffusion, but so what? Why is all this so important? Let's connect this all back to the real world and see why these tiny movements are the foundation of, well, everything. And here is the truly brilliant part. The total electric current in a chip isn't just from the electrons moving, it's the combined flow of both. You've got the negative electrons physically moving one way, and the positive acting holes appearing to move the other way. They work together as a team. It's like having two lanes of traffic on a highway instead of just one.
And that combined two-lane current is what makes everything we love possible. The ability to precisely control the flow of both electrons and holes is the secret sauce behind diodes, which are like one-way gates for electricity. It's the secret to transistors, which are the billions of tiny switches that make up every CPU and memory chip. It's how solar cells work, it's how LEDs light up. It all comes back to this.
So, if you walk away with just one thing from all this, let it be the super simple memory trick. An electron is a real particle. Think of it as a person, moving through the room. A hole is just the empty seat they left behind, which looks like it's moving in the opposite direction as people shuffle around.
So the next time you turn on your phone, you'll know. It's not just some abstract electricity. It's a beautifully coordinated dance between real particles and the phantom holes they leave behind. Our entire digital world is literally built on the elegant physics of an empty space. And now you know exactly how it all works.